Okay, in this video, we're going to take a look at a sample ladder problem. So as you can read this, you can pause this and read it, but basically we have a 10 kilogram ladder that's leaning up against the side of a building. And I kind of played around with the angle, but anyways, I just did this to get some different numbers. But the ladder itself is 8 meters long, then its height above the ground is going to be 7.7, and it's going to be 2 meters away from the wall. Now, if we look at this, it says a 70 kilogram person is now going to be standing on the ladder, approximately 1.9 meters up the ladder. So they're 0.5 meters horizontally from the base of the ladder, so here's 0.5. What are the forces exerted on the bottom of the ladder? This is very similar to one that's on our WebAssign. So what I'm going to do is I'm going to kind of redraw this and just deal with all the forces and stuff that's on it. So I have the ladder. I know that there's a force of gravity. I'm going to put that in red, acting on the ladder, and it acts at the center of mass. And so I have this force of gravity here. So F sub G, that's just going to be M times G, and since it's 10 kilograms times the 9.81, that's just going to be 98 newtons is pulling down. I also have the person standing there, and I'll draw them in real quick, but I have a force of gravity acting on the person. That force of gravity, the distance is 70 kilograms times the 9.81, that's going to give me force of gravity there is equal to 686 newtons. Now, other forces that are acting on this, I know that I have a force due to the wall pushing back this direction. So there's the force of the wall. And I also have a horizontal force, FH, horizontal force acted on by the ground. Kind of frictional force keeping that ladder from slipping out like this. And then I also have one other force, which I'll put in black here, the force of gravity. I'll put force vertical. It's the vertical force from the ground as well that's pulling it back up. Now those are all of the forces. Now please realize that I said that we're going to ignore friction up here. In real world, there would also be a force of friction pushing this back up. But for right now, we're going to ignore that piece. Okay? So now I have all of my forces. So the next thing I want to do is I want to set up my static equations because this ladder is not moving. And so I can talk about horizontal. If I look at all the horizontal forces, I've got the force of the wall pushing this way and the horizontal force from the ground that way. Since the object is in equilibrium, I can set those two forces equal to each other. So force of wall is equal to the force horizontally provided by the ground. Okay? Those are the only two horizontals. I'm done. If I look at the verticals, there's a few more verticals. So if I put vertical here, now I have the force vertical by the ground pushing back up, and then my two forces of gravity going down. So they have to be equal to each other. So FG person plus FG ladder. Okay, now those are all my vertical forces, 2 down, 1 up. Those have to be equal to each other because, again, we're in equilibrium. So right now I can find out force vertical. That part's easy. I've got the 686. I've got the 98. So I've got my force vertical. That's going to be a whopping 784 newtons. So that force right there is 784 newtons. Pretty simple, pretty easy. But I have nothing to find FW or FH. So now this is where I have to use torques. And what I'm going to do is I'm going to put my pivot point right smack dab here. Actually, I'll do it red. Right smack dab there. And the reason why I put my pivot point here is because that way now it eliminates FV and FH from being part of my torque equation because they are 0 meters away from my pivot point. So neither one of those forces are going to actually predict or produce a torque. And so my first torque, I look at, all right, so what ones are going to cause it to rotate clockwise? So do it this way. If I look, I have this force and this force. Both of those are kind of pulling down the ladder. That's going to cause it to rotate clockwise. So I'm going to start there. So my torques clockwise, well, that's going to be the force of the person times the distance the person is away from the pivot point plus the force of the force of gravity on the ladder times its distance away. Force of gravity ladder times its distance away. Force of gravity person. Okay? Now, what you have to remember on these two is that these must be perpendicular. So, because this force is pulling straight down here, I need to use the perpendicular distance. This part right there because that's the perpendicular distance between the pivot point and my force. Well, I already labeled that as being 0.5 meters. So the force of gravity of the person, which is 686 newtons, multiply that by the distance away, perpendicular distance away, 0.5 meters, that gives me that torque. If I look at this one up here, this distance from the force of gravity of the ladder to the pivot point, I kind of drew it up so I didn't overlap everything, but that's going to be, so if this whole distance is 2 meters, center of mass goes to the exact center, so this has to be 1 meter away. So I can say that this is 98 newtons times 1 meter. And so my torque, which is causing a clockwise motion, that's going to end up giving me, when I solve it out, to be 441 Newton meters. And you can check my math. Okay? Now remember, this has, because it's in static equilibrium, this thing has to be balanced by the counterclockwise torque. If I look at the pivot point here, the only other force that's acting on it to cause it to rotate back is F wall. And so the torque, which causes my counterclockwise torque, the force is going to cause my counterclockwise torque is going to be the force wall times its perpendicular distance away. Now, if I come back up to here, this is where my force of the wall is, X up here. Here's my pivot point down here. So if I look at this distance right here, I'm trying to sketch it in really lightly, that distance right there, that is my perpendicular distance, which I already labeled as 7.7. So the torque going back up is going to equal the force of the wall times 7.7 meters, because that's the perpendicular distance it is away. Now remember, these two have to be equal to each other. So I can set that up and say, all right, well, 441 Newton meters is equal to the force of the wall times 7.7. And so my force of the wall, I'll put it over here on the side, ends up being 57.3 newtons. And since the force of the wall is 57.3, the horizontal force provided by the ground is also 57.3. So I can put this off to the side. The vertical force from the ground, FV, was 784 newtons. The horizontal force provided by the ground is 57.3 newtons. That's how we go about solving this particular statics problem, using a combination of forces being in equilibrium and torques being in equilibrium. Okay. Now, if there was a frictional force up here on this ladder, then like we said before, then there would be a frictional force here as well. And now we'd have another upward force besides the ground one we'd have to take into account. And we'd also have to take into account the fact that this would also provide a torque as well. And its perpendicular distance then would be 2 meters. But we can expand that on that later. Hope this helps.